Hello, welcome back to a new video here on the Vertex channel in my D3D12Ez video series. Now in the last video we have taken us quite some time to get to know how to use the root signature a bit more efficient, or effective actually, not efficient, sorry. To use it more effective to add a descriptor table on it and to add a static sampler on it to basically allow us putting a texture in here, putting a sampler in here and using them both in the pixel shader to sample a texture, currently at a static position. And if I run that, well, we get nothing, because we haven't bound it on the CPU side. We have changed many things on the GPU side. We have changed our whole shader path. We have changed many things. However, we have not adapted our C++ runtime to kind of like reflect those changes. And that's what we're going to do in today's video. In today's video, we want to reflect our changes, and we want to make sure that we now bind the descriptor table that we specified in HLSL in the root signature, that we are now going to bind it in C++ to basically tell you, hey, this is the table that you shall use for texture access. Now, how are we going to do that? Well, I'm going to first show you how it goes in the theory, and then we're going to build all the infrastructure around so that we can actually support that theory. So in general, it's actually quite easy. You can see that we set it up our pipeline state like that. We set the pipeline state, and then we set the root signature. And somewhere down there, we basically configured our root signature. We configured the root signature, maybe let's do it like that. We configured our root signature by basically computing a color. I'm gonna put it in here. Let's put that like kind of like update. And there, we kind of like specified a color, we puked the color, and then we set it is a constant. And that's basically what we need to do for the table as well, because the table, we are going to reconsider our root signature, is now at slot 1. At slot 0 we had the color, and at slot 1 we had the table. And now what we need to do in main is we basically need to bind at slot 1, and we need to bind the table. So the usage actually quite similar. Set graphics root is kind of like the prefix, and then what we want to set is we want to set a descriptor table. So set graphics root descriptor table. Now again, because I'm a bit zoomed in here, let's peek inside of here so that we can see how it works. You can actually see that this function is a rather simple one. You just need a root parameter index, which is now of course the 1 because it's now at slot 1, and you need a GPU descriptor handle, the base descriptor. And the base descriptor is basically the first array entrance. This is kind of like the first kind of like index of the array of the descriptors. Now, how do we get the GPU descriptor handle, and how do we obtain the descriptor to that, or how do we create a descriptor? Well, descriptors are created in a descriptor heap. We already have used a descriptor heap inside of our window. I told you that we need the descriptor heap for render target view descriptors, so that we can basically have a description on how our frame buffer looks like, how our window buffer to which we're going to draw looks like, to be able to bind that one. And that's kind of like the same idea that we have here now with the texture. We need to have a descriptor heap, and we need to set the description on the descriptor heap to kind of like reflect the way how we access the texture. And that's basically what we need to do now also inside of our main. We need to create ourselves a descriptor heap, and inside of the descriptor heap we need to describe our texture, and then we can reference the descriptor heap inside of that function to bind it. Now, how do we do that? It's actually not that hard. We created a PSO here. Let's maybe create it, the shaders. There was some copying going on, and here's the thing, the texture creation. And then we're gonna say descriptor heap for texture. And since we could have multiple on them, yeah, I'm just gonna add an S here. So how do we create that descriptor heap? Well, there's of course a description for that. Descriptor heap description, DHD. I don't think that we have this name used here yet, and you know that that's not quite a good idea to always name these a bit odd, but yeah. So let's take a look at how this descriptor heap works. We already have used that, and I didn't want it to completely go in there, but it's okay. We already have used that inside of the window.cpp somewhere. DHD, somewhere down there. Here, the RTV heap, descriptor heap description. We have already used it in here to kind of like have as many descriptors as we have frames. And now we basically do the same thing, but for textures. Now, instead of our main, let's quickly now paste these ones in here, and let's do it like that. So, oh, I've removed that one above here. I didn't want it to do that one. I just wanna this DHD. equals to that, and yeah, maybe let's add. Now, let's see. All right, so the first thing that we need to specify is the type of descriptors that we put in here, and I don't know. Come on, IntelliSense, give me back my autocomplete. I hate it. Alright, so now we should get back our syntax completion, there it is. And now we can see that we can again specify multiple heap types. We used RTV for render target views, and DSV is something that we're going to use in the future. Now you can see that there are two more types that we haven't used yet. We can actually create a descriptor heap for sampler, so if you don't want to use a static sampler, if you want to change it at runtime, you can basically create a descriptor heap with samplers on it, and you have the option to create a descriptor heap for actual shader resources. Shader resources are constant buffers, shader resources themselves, and the unordered access views. So we're gonna create a descriptor heap that can hold all of these three types. So we're gonna create that one. How many descriptors do we need? Well, actually this doesn't matter, but we can provide 8 in here just to play a bit around with these numbers, and I can show you on the graphics debugger what you can see there. Now, the next thing that we need to specify is how the visibility of that heap is. We need to make that heap shader visible because we want to actually bind that heap to the pipeline. And if we want to bind it to the pipeline, it needs to be shader visible. Then node mask again to 0 because we're not going to use any specific one. Then let's create a com pointer. A D3D12 descriptor heap. We're going to call this SRVD heap, or actually SRV heap is actually sufficient because this is a view and views are descriptors basically. So we can do it like this. SRV heap, that's correct. Then we need to get the context, get our device, and ask it to create that heap for us. So create the descriptor heap, please. Then we need to provide the DHD, the description, and then of course I cannot see the arguments because I'm zoomed in. We have the IID PPV args. That's the only thing that needs to get in here. So we're going to provide our pointer IID PPV args to SRV heap here, and now we have the descriptor heap created. Now the only thing that's now required is to now actually create the actual views. So now we actually need to create the shader resource views, because just because we have the heap doesn't mean that the view is in existence. Having the heap means we have the memory allocated where we can place these descriptors. And now we need to actually place the descriptor, the shader resource view, by asking our device to do it. So currently you can see we just have an empty heap, and now what we want to do is we now want to create a shader resource view. Now, how do we create a shader resource view? First, we need the resource pointer that we want to use. So that's our texture. Then we need a descriptor, and I think the handle, as far as I know. Yeah, you can see that you need a resource, you need a description of the shader resource view, which you can actually put in optional. So you can see that there's an in optional, and the first one is also optional. If you are providing a resource and you don't want to change anything on the configuration of the shader resource view, you can create a default one by just providing null pointer. And then you need a CPU descriptor handle that basically says where to put the descriptor. Now, out of curiosity, I'm just going to also use the descriptor here now. This is our SRV basically. And I'm going to describe that one so that you can see what's in here and that you get a bit of more insights on what this does. If we peek in here, you can see that there is a format that you need to specify, a view dimension, and you need to have a 4-component mapping, and then you can define more information based on what kind of like view dimension this is, so if it's a texture 2D or so on. So the first thing that we're going to provide is the format. This is basically what you can do is you can actually load a texture of a certain format and then access it in the view with a different format. So you can have like a texture that is of a format uint4, so 4 unsigned integer values. And you can have a one view that kind of like uses this with like 4 floats, and one view that uses this with 4 uints. So you can have 2 views to the same resource, and the views basically have different kind of like formats, and then you can access them in multiple ways. In our case, we just want to take the format that we have gotten here. So that one placed in here. Then we need to have the view dimension, and the view dimension is, come on, Visual Assist. Now the view dimension is going to go to texture 2D because we have a 2-dimensional texture. Then we had the shader 4-component mapping, which is going to be the D3D12 default shader 4-component mapping. This is a macro, so we don't get autocomplete here. This basically means the default accessing. Actually, what I can do is you can swap color channels. 4-component mapping means float 4 basically, because we at the maximum have 4 components in the texture, and in any resource at all, every resource that we're going to have has 4 components, and you can actually specify the way how they are used. In this case, you can see it's basically the encoded mapping 0, 1, 2, and 3, which basically means that all channels are mapped as is, and you could basically change channels here. So if you have a texture that's not RGB but BGR, for example, then you could change the way that the mapping is done by basically swapping around the kind of like the order of the bits with this view, because the view is basically influencing that. The next thing that we want to specify is all the specific data to a texture 2D. You can define the MIP levels that are used for the textures. This is like one that we have. You can specify most detailed map, which is then the map 0, because we have 1. The most detailed one is now the array index of 0. Again, if you have multiple map mapping, you can basically limit how map mapping works on the GPU by displaying kind of like the most detailed one to kind of like limit it from kind of like overshooting. Again, map mapping, something that we might gonna discuss in the future, but for now I'm basically just gonna set them all to a bit of the default values. You can define plane slicing, I think it's also an integer, and so on. So you have multiple things there. I think one value was there as well, like this resource LOD clamp, which is I think a float as far as I'm concerned. Yeah, it's a float. And you can basically define how that texture would be accessed. We can also provide that run now, however, it's not that crucial that we need it. Now, the last important property is now the actual handle that you want to put it to. And actually what we're just going to say is we're going to ask our heap to get us the first handle. Now, if you have multiple textures, you of course need to deal with these, and you need to make sure that these handles are set to a correct value. Basically, again, we already used them at the window.cpp by the getBuffer function. Where is the getBuffer function? Begin frame, end frame, get buffers. You can see that we basically retrieve the buffers by, where is it? Get buffers, create render target view, mrtv handles at index I, so I already retrieved them somewhere else. We basically retrieved them, I think, in here. Create handles to view. Okay, so you can see that we have retrieved the first one here, and we retrieved the increment size, and basically what we have done is we have offsetted them by the handle increment times I to the already existing pointer inside of the handle, and we basically move the handle around. If you have multiple of them inside of main here, if inside of the textures kind of like descriptor array, then you can also use it here, but in this case we're just going to put in one texture, so I can get the CPU descriptor handle for the start, and I don't need to modify it. Now you can see that we should have created a descriptor handle, not a descriptor handle, that we now have used a descriptor handle to create a shader resource view. And now the shader resource view is created on the GPU, and now we can use it on the GPU. Now how do we use it? Well, we're going to scroll down here inside of here. And when we're now going to bind the table, we need to bind the GPU-sided handle. So on the CPU side, we specified it for creating that, and now we can get the GPU handle. So up there we had get a CPU, because on the CPU, we use it with the CPU descriptor to create the view on the GPU. And now we are getting the GPU-side descriptor handle to then, during execution of the root signature, have that kind of like root argument pointing to that table on the GPU. So kind of like GPU, CPU sided. And this is now binding the array to the descriptor table. And if I now run that, you're going to see that's of course not going to work, right? Because it would be too easy if it would work like that. Right? We might get a device removed, a crash or something, or we might just going to get black again. No, we're going to get, an exception. Amazing. So if we go to output, we probably, did we get device removed? No, but we get a bit of an information on what's going on. Yeah, okay. This is the interesting one. Set graphics root descriptor table. You can see that no, CBV SRV UAV descriptor heap is currently set on the comment list, so setting a root descriptor table handle is invalid. So we had a problem here. Now, how do we fix that problem? Well, basically what we need to do before we can use that heap, we actually need to bind that heap. We need to bind that heap on our pipeline with our pipeline set, kind of like we need to bind that heap to the GPU. So set descriptor heap is the function that we need to call, and in that function we'll basically set a certain amount of descriptor heaps that we want to bind. I just want to bind one descriptor heaps, of course in plural, one descriptor heap, and I'm going to provide my srv heap in here. And this function is now basically binding that heap. It's basically telling us this is the heap that we want to use, and that's very important. You can't bind two heaps of the same type. You can only have one heap of one type bound at a time. So if you have like concept buffers, shader resource views, unordered access views, and you use multiple of these tables, you cannot have an own heap per table. This doesn't work. You need to have like one big uber table and then sub-allocate ranges out of them, and then use the sub-allocated ranges inside of that, these calls, to kind of like offset them in like one big table. And if I do it like that, we should probably now get everything working. Let's press a 5 and see what we get now. If we are getting something, or if we need to tinker a bit around with those values, but as you can see, we get it working. It's no longer black. Well, it's no longer black because we are now actually taking a pixel value from the texture. However, as you can see, well, everything is still one solid color, and this is of course the case because we are just using one single pixel value. If I go back to my pixel shader, you can see that we are just always using sampling at 0.5 and 0.5, which is basically the center of the texture, and we could go now in with a GPU debugger and debug the shader and step through the shader, and you're gonna obviously gonna see that it's always gonna sample that certain location. And if we're taking a look at the texture at that certain offset, and we are using the same algorithm that the GPU does for filtering, because that's not actually a valid pixel value that I'm addressing here, you would then of course see that we are actually getting the correct pixel value for that coordinates. However, we don't like that. We actually want to modify these. It's not nice like that. We want to modify them. How do we modify these? Well, there are multiple ways of doing that. However, we are going to do it in the like a bit easier way. Now, the first thing that I'm going to do is I'm going to rewrite our vertex shader. Now, how do I want to rewrite the vertex shader? Well, you're going to see it. The first thing that I'm going to do is I'm going to change that float void to void. I no longer want to return something in the shader. Why do I no longer want to return something? Because it doesn't work the way we're going to rewrite our shader. Because normally what you would need to do if you're returning multiple values from a function, you need to return an object. You would need to define a struct, in this case on HLSL, and return a struct. However, I don't want to go into too much hassle now of defining structs and building complex render passes. I want to keep it simple. So I'm going to use another way of handling parameters in HLSL. I'm going to add a prefix to them. Now, our position is an input parameter, so I can add the keyword in. I can tell it that we have an input float to position that's bound to the semantic name position. And the same way we can also handle output. So what we can actually define is I can define an out float for, and I'm gonna call that one SV position because it's now the system value position. Could also do a so-called in-out and provide them as an input and an output, but that's a bit harder now. And now what I want to do is I basically want to now, instead of my shader, assign the SV position to that computation. And this is actually working. Now, I don't know why HLSL sometimes is expanding that line above here, but that's kind of like okay. Now, basically what you can see, we have now an in and an out parameter. Nothing has kind of like changed from the code, only the way we kind of like handle our parameters. And if I recompile that one, you're going to see we get the exact same result. So why do I need that? Well, I need that because we're going to have now multiple input and multiple output parameters from now on. So we're going to have input parameters. So let me prefix them in. And we also now on also going to have output parameters. So we're going to have input parameters to our shader and output parameters to our shader. Now, since we want to access a texture, we need to know where to access these textures in the range of 0 and 1. So instead of now actually going into the hassle of doing some complex computations to know out of that position where kind of like the related shader position is, the related position to that in here, we actually gonna now provide a second parameter for the texture coordinates. So we're gonna have another input of float 2. No, in. I don't know why autocomplete is a bit scuffed with these in and out values. Now, what we basically gonna have is a parameter called UV. These are the so-called texture parameters. So UV texture parameters, and you can actually define these as in out as well, but we're gonna have them simple as possible. So here we're gonna have texture coordinates, text, coords. This is actually like the common name how you do it. Autocomplete, of course, capitalizes this. I'm gonna just call them UV texture coordinates. And maybe I'm not gonna call this SV pos, I'm just gonna call this O pos for output pos. And now what we're gonna do is we're gonna take these texture coordinates and actually we're gonna just pass them on. I'm just gonna copy and paste what we have above here. I'm gonna copy paste this down in here, change the into out, and change the name to OUV. And what we're gonna do in here is we're gonna say that OY is autocomplete so scuffed. There we go. OOV equals UV. So basically what we're gonna do is the position is calculated based on XY as carefully like auto-completed, there are values added to that, and the UV coordinates are just passed on as they are. And the UV coordinates are texture coordinates that we then can feed into our next shader stage. So that's kind of like the signature that we have. We can now go to our pixel shader, and inside of the pixel shader, we can now use these ones as parameters. And I want to refactor this to the same usage. We're going to have some input arguments. In float to UV, or in this case it's called OUV because it's like output. And no, actually we just need to match these. I think it's okay to name them like that because they are linked with text coords. That's actually okay, should be okay. And what I'm also gonna do is I'm changing that to void, and then we're gonna have a out, and we're gonna have an odd. Out, I hate it, out float 4, and we're gonna call that one pixel because it's not a pixel data, and the pixel is the SV target. And now what I can say pixel is equal the texel's RGB values and the alpha value of 1. And now instead of passing this like hard-coded value, I'm gonna directly pass in the UV texture coordinates. Now the only thing that now needs to be done is our input layout on the CPU side need to be adjusted so that it reflects the new layout of the UV coordinates. So we now on the CPU side also need to pass UV coordinates to the vertex shader, because as you can see, position UV, this is how it flows into the vertex shader now. How do we do that? Well, it's actually quite simple. We just need to adjust a few of our states. Let's start and let's scroll a bit around. Now, first of all, our vertex needs to be expanded by the UV coordinates. So now I've added UV to our vertex. And our vertices, of course, need to change as well. I'm just going to provide the good old 0.f value. Actually, let's maybe now provide a bit of a different value so that we maybe can see something change. So basically, we're gonna add the UV coordinates to the initialization of the triangle, and then the only thing that's left to do is we need to provide a text coord here. We need to basically adjust this in here as well. And let's quickly peek inside of how the structure is laid out so that we know how to change. Semantic index 0 is still correct because you can actually have an array of text coords and 0 is okay. Format to floating point values, it's okay. Input slot is okay. Aligned byte offset is not something that we need to change, because if we have them both at 0, it means that they are kind of like overlapping each other. So basically what we have is we have the size of float times 2. This is the offset that's going to be adjusted in here. And all the other values are actually good. Per vertex data is good, and that one is, I think, instance step rate or something like that. What was it? Instance data step rate, since we are not using classification on a per index data, it's set to 0. And now the text code is already passed in here, and I think if we have written our code well enough, this is the only thing that we need to change. Let's see what it does and if we are getting something. And we don't. Okay. So what's the problem? Vertex shader, pixel shader, linkage error, signature between stages are incompatible. Is defined for mismatch hardware registers because between the output stage and the input stage. Interesting. What's the problem? Something has gone wrong. Now, basically, our shaders were valid and our C++ code was valid. Now, the only thing that now has happened is that the signatures between the vertex and the pixel shaders are no longer matching. The text coord is UV in float 2. It might be. Let's rename them. I'm not sure if this is the problem. Maybe we also need to change if we change the register to put the text coords first, because actually SV position is something that's also accessible in the shader. SV position is actually something the pixel shader can observe as well. So it might be required to keep them in order, because basically the order matters on the memory layout. So basically what's happening with the in and out, the GPU is creating a struct out of these. And if the structs don't match, if the signature don't match, you have a problem. And then basically at runtime, when the pipeline state is created, the two shaders are taken, passed to the driver, passed to validation, they can no longer make one struct out of these. Yeah, if I change the order, it works, because basically it is important. It is important that order here, first the text chords, then the position, is the same in the pixel shader. And if we are omitting that, if we are omitting the text chord here, if we are omitting the text chord, not the text port, that as we position, if we are omitting as we position, it would be as if it would be below the text chord. And if it would be below the text chord, it's no longer matching how it's outputted in a vertex shader. So normally you do structs. I'm just doing that out of simplicity, and you can see that I've fallen on my head with that. It's not really taking into account simplicity. It's not simple to have these orders in mind, so a struct would be more beneficial. I'm not going to change it for... I'm not going to change it for this video here now, but we're going to change it in the future. I'm going to promise. Now, what we need to do now is, of course, we now need to modify the UV coordinates, because they are not correct. Now, how do you define UV coordinates? Well, normally you're going to have mappings. If you have a proper three-dimensional application, if you're using Blender, your artist is going to do the texture mapping, and the texture data is basically flowing out of the FBX of the Blender file, of the OBJ, whatever. Now, in our case, we need to do the texture coordinates manually. And I know how to do that because I've authored the texture. Now, as you can see, -1, -1 is the bottom left, and the bottom left texture is 0 and 1, or the texture coordinate is 0 and 1. That's the bottom left. Then we have 0 and 1. This is kind of like the center top. The center top is a value of 0.5 and 0. And the bottom right is a value of 1 and 1. And the GPU is going to interpolate between these values, and I'm going to show you why these values are as is if we are on a graphic debugger. And if I now run my application, you can actually see that we now have the triangle on the screen. And the all-seeing eye is looking at us, and it's like a big meme that we have programmed, right? We have programmed hours and spent hours into a tutorial series writing code to get the meme all-seeing eye triangle on the screen, right? Nice. Amazing. All right, let's press Alt+4 and get out of it. And let's now go into like something like inside graphics. In a graphic debugger to see what's actually going on, and maybe explain this one more time so that you understand what's going on. Alright, before we can do inside graphics, of course, I need to make sure that I do once a release build so that everything is compiled and released, because it's not compatible with the debug layer inside graphics. So let's recompile it. There it is. And let's quickly start it here and see what we got. Let's wait until we get the window that we don't care about, and let's wait a few seconds. There is the all-seeing eye. I can hit F11 to do a frame capture, so I'm going to hit F11, and there it is. We have now a frame capture, and now you can already see I have my replay bar here, and I can see all the events from the back, from the invalid buffer to the cleared buffer, to the drawing of the triangle, to the present state of our image. You can see this is the triangle. I can move it around. I can inspect the triangle, the pixels, everything. Inside graphics is really, really helpful for that, but that's not really what we care. We care about inside graphics in here. We don't care about the resource because they haven't changed. What we care about is how this is getting serialized to the GPU, how it works step by step, and how our pipeline is arranged, how our descriptors are looking like. Now what you can see is we started with a resource barrier, clear render target view. So basically we set our resource to be a render target, then we cleared it to this odd value that you can see in the background. Then we set the buffer as a render target. We set it a pipeline state, and if we are setting a pipeline state, we need to set the root signature associated with that pipeline state as well. If we have a root signature bound, we can set descriptor heaps that are used for the root signature. We bound our input layout by providing the vertex buffer and the primitive topology. We set it up the rasterizer, and then we configured our root signature by providing a float value for actually the color of the triangle that's no longer used, and we provided a descriptor that's kind of like used as a base descriptor for our textures, and then we were able to draw and then put again a texture barrier, a resource barrier, to make sure that everything is good. And now what I want to actually take a look at is I want to go into the frame debugger, and I want to go to D3D12 descriptor heaps. And if you're going into descriptor heaps, you can actually see what's going on in here. You can see that there are a bit of heaps that are actually named inside graphics. And this is basically just something that Inside Graphics uses internally to gain a bit more access to the descriptor heaps that we are kind of like inspecting. Now you can see that there are two more descriptor heaps, the descriptor heap 1 and 5. These are the ones that we have created. The RTV descriptor heap, that's the descriptor heap that we use for our render targets, the frame buffers on the window. And we have a descriptor heap of the type CBV, SRV, and UAV with 8 descriptors, which is the descriptor heap that we used to describe our texture. And you can see that descriptors 1 to 7 are invalid. They have never been set. However, you can see that the heap entry here at position 0 was used for our texture. So you can see what the format is of the texture, the view dimension, how the component mapping is done, how the MIP mapping is done, the clamping is done, and you also have a reference to the texture that's actually bound that I can click on and see the texture itself. And if I hover over the texture, you can see we see like all the coordinates that are going on, the color values that are going on, and how this is all like getting together. We have a bit of layout on the texture, but we already talked about that one. Now the mapping, of course, is now working like that. I've hard-coded like the values inside the vertex buffer, and to understand them, you kind of like understand that this was the first vertex at the bottom left, and the bottom left vertex is corresponding to that pixel value that we wanted, which in UV coordinates, X direction 0, or U direction as it's actually called, and with textures it's set at 0, so it's here. And then the V direction, which is kind of like the Y direction, it goes to the bottom and it's 1, and we are at the right offset. Now the next vertex was above here. This basically is the vertex that corresponds to the center top, and you can see that I've used the values X of 0.5 or U of 0.5 and V of 0, so we are ending up here. Course, again, always starting here at the top left on textures. Now on the bottom right of the triangle, we had the coordinates 1 on X and 1 on Y, or X 1 and 1 on U and V, which is also here the correct offset on the texture. Now, how do you know these offsets? Well, I know them because I know the texture. You can see that's actually stretching a lot the texture. It's not aspect correct, and it's basically because we are stretching it to the screen resolution. Now, again, textures always at 0.0, and then they expand in U and V directions. And that's actually quite simple. Now, we just defined the data between all of these vertices, and basically what the GPU has done is it has interpolated between the 3 vertices for every pixel, and this is why every pixel is correct, right? We have a shader, it has a dedicated value on a per pixel base, but we have defined 3. It is a bicentric system of order 3. A trilinear system, can also call it like that, and the trilinear system is solved by the GPU for every parameter, and the value is interpolated. As simple as that, and this is how it works, that we get color values for each pixel. And I think that's it for today. So now we see that we have a nice little triangle on the screen. Thank you for watching. See you in the next video. Make sure to like and subscribe, and have a nice day. See you in the next one. Bye.